In this video, Jens and I are presenting our paper, Gradient-Based Analysis of NLP Models is Manipulable, which was work done by Junlin Wang, Jens Tolles, Eric Wallace, and Samir Singh at UC Irvine. Gradient-based methods in NLP have seen widespread use for making sure the model is doing the right thing before deployment, to increase human trust in the model, and for diagnosing model biases. They are also considered more faithful than other black box explanation techniques. We show some gradient-based interpretation methods on the right. We examine science map and attribute importances to each input token. We'll also look at input reduction and hot flip, which perturb the input until the prediction changes. We show that gradients can be manipulated and be made completely unreliable indicators of the model's behavior. In other words, we create a model which maintains the original predictions but has manipulated gradients. Here, we demonstrate some examples of our method. We consider a BERT-based classifier trained on sentiment analysis. For saliency maps, we see that much of the attribution has drastically shifted to stop tokens, which is the target of a manipulation here. In addition, we see that input reduction for the merge model leaves only irrelevant stop tokens. Finally, hot flip perturbs stop tokens like the, and off.
We show this can be done by training a facade model, which is trained to have misleading or irrelevant gradients, but uniform predictions, and merging it with the original model. As you can see in the figure on the bottom right, the green model is a general off-the-shelf classifier and is merged with the red facade model in the middle. The resulting merged model keeps the same behavior as the original model since the output of the facade is kept uniform. However, the gradients of the merged model will be dominated by the facade model. This fools popular saliency methods such as gradient, smooth grad, and intergradient gradients, though the last one is more robust. This also causes gradient-based analysis techniques such as input reduction and hot flip to identify unimportant or targeted tokens as highly important, as was shown in the previous slide. We present our results on saliency maps in the first token setting. In this setting, we train the facade model to have high gradients on the first token. In the table, we show results for 3 different tasks: sentiment analysis, NLI, and question answering. As you can see from the table, the attribution percentage on the first token is significantly higher after the original model has been merged with the facade. The performance of each task stays the same. This shows our method completely fools saliency maps. Please refer to our paper for more results. In summary, we demonstrated that gradient-based analysis techniques can be manipulated without hurting the performance of the model, which implies that gradient-based analysis techniques are not as faithful as commonly perceived. We also hope to encourage the development of more robust analysis techniques and methods to detect adversarial modifications. Thank you.